Hey YouTubers, if you're looking for the Debunkified channel, then you found the right place. In this video, we're going to be talking about a circuit that seemingly takes 1 watt in and puts out 2 watts out, that we can read with meters. Now, the perception of it is a bit strange, and so this is what we're going to be talking about, is exactly how should we be perceiving this input with 2 outputs coming out. You know, this kind of reminds me of the double slit experiment, in that if you don't know what that is, you can go YouTube it if you want, and I'll tell you a little bit more about it. But essentially, what the 2 slit experiment is it uses an electron beam and 2 slits, and it basically is scientific proof that simply by observing reality, we can collapse wave functions of the mass of that reality and change it simply by observing it. So this is kind of like what this reminds me of, and so I know it sounds kind of wacky, but it's the closest thing I know how to describe it because of the perceptions on how we should look at this circuit exactly. So bear with me, and let's start with a couple pictures. Okay, let's take a look at this circuit right here. Here we have a DC to DC converter that's being powered by a power supply here. Okay, and this is the input wattage. It's at 100%, of course. Okay, and then the job of this DC to DC converter, okay, is to convert energy through the use of a magnetic field. And so it outputs 95% of the energy to run these lights. Okay, these lights, LED lights, are shining on some solar panels, and so we get another output out over here. Okay, now what I would like to say here is that this DC to DC converter is indeed a workload, okay, because it's doing the work of converting through the magnetic field, and so it's outputting energy. Now the energy that it's outputting is the exact same energy that came from the power source. Okay, all of this is normal and fine so far. We do this all the time with power supplies, and even a Bedini circuit does this. It forms a magnetic field, and then the magnetic field collapses and then shoots out a large amount of energy that we used in the first place, most of the energy. So our load is these LED lights are running off 95% of the energy, which we can use. We can see this with meters. There's meter reading power input current coming from the power supply into the our circuit, our converter, and then the converter shoots out almost 100% of the energy on the load here that the load uses up. And of course we could put a meter here to read current going into our load, and then also, of course, if we had enough meters to read this, then we could put a meter right here on the positive and negative and read the voltage, and then find out how much wattage is flowing. So the point is, we have wattage flowing here that's being used up, and then wattage flowing out, which we're also utilizing to run these lights. Now these lights are outputting light, okay, onto these solar panels, and these solar panels are outputting onto a load, and so we get a second output. Now we would not want to sit here and say, okay, since this is the final output right here of 1%, that the entire system is just 1% efficient. We can't ignore this 95% efficiency that's going on right here, or this wattage flow in the form of wattage that we are reading with a meter, with current flowing through the load and voltage across the load. So let's take a look at this extremely simple circuit right here. It's just a power supply running 2 LED loads, or it could be just one load. This is what most of us do. This is a normal circuit. Most everything does this. It just takes the power from the power supply, runs the load, and then just wastes away all 100% of the energy and not put out any kind of electrical energy. Now the LEDs do have an output of light and heat, okay, but it's not electrical output. So the efficiency of this circuit, which most of us use on all of our devices and machines and appliances, TVs and so forth, is 0% efficient. Okay, now we add a DC, the DC converter. Okay, this converter can be considered a load, and its job, since it's a load, you know, it is a real workload. It does the work of converting energy going into it through the use of a magnetic field, and then outputting electrical energy in return. Now, it's the same exact energy that came from the power source. It's just stored in the magnetic field, and then of course the magnetic field collapses and gives us back almost all of the energy that went into it in the first place to run our loads. So this is recycling the energy once, okay, just once. And we can read that with a meter as well. Okay, so we're reading input and output. Now if this, for the sake of illustration and example, if this was 100% efficient, then 1 watt of energy would go in and 1 watt would come out, and nothing more. It'd be perfectly 100% efficient, and we would be able to read this with meters. Okay, so now this is where it gets a little bit tricky. We now add another converter, okay, and we're basically creating 2 magnetic fields around this one and the second one. And if we take the output of the second one, okay, it's going to be, you know, the efficiency is going to drop a little bit. In reality, in the real world, this output over here is going to be 95% of this 95%, so we're going to really end up with 90%. But the perception that I'm trying to realize and understand and interpret a little bit better is we have a meter here reading actual wattage. Excuse me. Okay, and there's an actual wattage flowing here, and it's 95%, or in a perfect system 100% what's going into it to run this load. This is another load, so I consider these loads that have outputs, okay, and so this is outputting in a perfect system another 100% that we can read with another meter. So we got 2 meters here reading 2 outputs. So exactly how do we consider perceiving this? Do we take our 90% here and add it to our 90% here for 185%? If it was a 100% perfect system, then this would be 100%, this would be 100%. And if you add the two 100% together, you would have 200% for just 100% going in. Now, what sense does that make? Is that really happening? I mean, we really do have 2 meters here reading current going into this load, and then current coming out and current going into this load. along with the voltage across this load and a voltage across this load. So exactly how do we look at this? I mean, it's real, it's there, it's really happening, and it's a true wattage flowing through this load and then through this load that we're reading with two completely different meters. Now, one thing I would like to say is the energy of the system, I don't think increases, but yet that's another perception that is, I just don't get it. If we put capacitors here, okay, and we stored 100% of our energy, let's say 1 watt went in right here, and then 1 watt came out, and we stored that 1 watt of energy, okay, not 1 watt of energy, just 1 joule of energy, because joules are energy. Now, energy, okay, is the potential to do work, and 1 joule of energy is actually equal to a 1 watt second. So if we stored 1 joule of energy, we're storing the potential to do 1 watt's worth of work. Okay, so we can do 1 watt worth of work off the first converter's output. We can save the potential to do 1 watt's worth of work, and 1 joule of energy, let's say stored in a capacitor, then we can use it again. Okay, it will deplete, yes, it'll go away, but then it'll basically reappear as another joule of energy. It has the potential to do 1 watt's worth of work again. So we're most definitely getting like 2 watts worth of work. Wattages, it's actual wattages that we're reading on 2 meters out with just 1 watt going in. And so there's 1 watt going in here, 1 watt coming out, and 1 watt coming out again. So what is that? How do you explain that exactly? So let's move on to the videos, and so you can see what I'm talking about a little bit more clearer. Okay, so we're going to do an efficiency test on this DC to DC converter powering this LED lights. So we're going to do that first by reading voltage first. Okay, that's what we're going to do. I'm going to have to make another clip. Okay, so don't freak out. I haven't changed anything. I had to do that because I had to change, save space and change out the meters to read current. But we're reading voltage first. This is the power supply we're using. It's just an AC adapter, or just a power adapter that's putting out about 12 volts DC. So that's what we're going to be reading on the input first. Okay, so this is the output voltage run across this LED load. Okay, and this is the input voltage going into our circuit. Now I'm writing these down on paper, the input and output voltages. So the input voltage is 12.15 volts. Okay, and the output voltage is 12 volts. Right on the dot. So I'm going to be writing that down so we can look at this all at the same time. Okay, so now we're going to be reading the input and output current. And this is just explaining how it's read by putting the meter in series on the negative side there, in between the negative of the power supply and the negative of our first converter. That's just to show that that's how you read current, basically, is just putting the meter in series in between either the negative side, which is what this is in this case, or you can put it on the positive side And you do the same thing on the output. Okay, so now it's time to read. That's our input current of 665 milliamps, or 0.665 amps. So we're going to write that down. And again, 600, and it dropped 664 milliamps, or 0.664 amps. And you multiply that together, and the output is 634 milliamps, or 0.634 amps. So I'm just writing that down so we can see all this at the same time. Those are amps right there. Now we're going to go ahead and we're going to calculate the wattages for these, and then also find out the efficiency of using just one converter. Okay, so now we're going to calculate the efficiency. It's very easy to do. You just multiply the voltage by the current to get your wattage, and then let's do that right now on our good old calculator. So we take 12.15 and we multiply that by 664 milliamps of current. Okay, which is right there, and that gives us 8.06 watts of input power. So let's commit that to memory, because we're going to need to divide into that later. And then we do the same thing with our output of 12 volts times 0.634 amps, or 634 milliamps. That's 7.61 watts rounded up. Okay, and that's our output wattage, 7.61 watts. So we divide that into 8.06 watts, and we get a COP of 0.94. So we just multiply that by 100%, and as you can see, we have a 94% efficient circuit and device going on right here. So the converter is 94% efficient. Okay, so this is the circuit I was talking about with the solar panel. Okay, and in the DC to DC boost converter circuit that outputs almost 100% of our energy into our LED load, and shining on a solar panel. The solar panel is then can be running another load, but I don't have a load on it, so it's just putting out some voltage. There's some ambient light in the room, and so we can do this in a dark room, and get rid of that. But the point is that the LED lights are shining on the solar panel, and the solar panel is another load apart from the fact that the LEDs are a load. So we have like two output loads. Now the light coming off the LEDs is just light, so there's no way I can really reflect back to the power source here and pull more current from the power source. So I just want to make that clear, that we really do have two different outputs, and we can relate to that as the converter doing the same thing. Alright, so let's get this started. Let's turn it on so you can see exactly what I'm perceiving as far as the DC converter doing the same thing. So here there's input current, there's power going into the circuit. We got an LED that's running off almost 100% of the energy going into it, namely 95%. And also we have our LED light shining on a solar panel, producing some voltage here. I can shine it directly on here so you can see that it is indeed a separate load producing its own voltage off the solar panel. If you had a load on there, you could run that load, but it wouldn't be very much. In practice, you'd really be getting less than 1% of your output there. It'd be 1% efficient electrically. So it's not a good conversion process in the real world. It's very poor conversion from the light of the LEDs onto the solar panel. But the point is that there is indeed, here I put it on amperage directly, short-circuited the meter directly onto the load, directly from the solar panel. So the voltage is going to be extremely small, just to pull up this current. But you can see there is current on the load as well, so there's voltage and current, or wattage, and this is just to show that there is indeed a separate wattage, apart from the fact of our LEDs running off of 95% of the energy transferred from the first converter. Okay, so here's the circuit I was talking about with the two DC to DC boost converters back to back. Okay, now these converters, I personally consider them as loads because they are doing work, but I consider them as loads with outputs. Now, if I had enough meters, I certainly would be showing all these wattages flowing at the same time, but I don't. So you'll just have to take my word for it, because it's really happening. So right there, I have a meter just reading current. Okay, but you can have another meter across the loads. That's the meter reading current. You can have a meter reading voltage across the load, the converters, and define wattages as well like that. But I only have 2 meters, so that's all we have to deal with. So that's what we're going to use. Have another meter on the output, negative side, reading current going into the load. Again, you can have a meter going across the load to read the voltage. Ultimately, when you multiply the voltages by the currents, then you'll get wattages. So this is just basically to show that there is indeed 2 wattages flowing on the 2 outputs. One flowing in between the output of the first converter and the output, or the input going into the second converter. It's an actual wattage flowing there. There I'm reading current only, but it's a wattage flowing right there, and there's also a wattage flowing on the final output there on the lights. So how exactly do we perceive this, and what do we call that? Now, some electrical engineers will say, okay, you take the final output of 90%, or it's going to degrade a little bit as it goes down the line because of resistive losses. So the first output will be 95%, and the second output is going to be 95% of the first 95%. So really it's going to be 90%. So do we take that 90% and add it to the first 95% to get a total of 185%? Because there really are 2 watts flowing right there. And if that was energy saved in a capacitor, yeah, the first magnetic field would spit out 1 joule of energy. You'd save it, it'd be right there. But then you can use it again and transfer that 1 joule and get another 1 joule basically, or another potential to do 1 watt's worth of work in another second of time. So chew on that for a little while, and maybe leave a comment. If you're new to the channel, please subscribe. Please share, because if you're tired of spending money on gas and oil to fuel your archaic propulsion systems, please share this with your friends. Thanks for watching.